recording. So this lecture is about control. Okay, so what do you think is control? I mean, everybody uses the word control in some way or another. What is your understanding of what is control?
It's if we have a plan, we have to introduce some
changes. So if we can change things or parameters in our own will or like intention, so this is like controlling things.
Okay, so you have control is related to influencing things such that you follow a plan.
Okay.
Yeah, exactly.
Okay.
Yes, exactly.
We can say that. We can say that. No. For instance, if I have some chemical reaction, and I want to keep the temperature still. Okay, there is one approach which is keep things adiabatic, but it never works because there are losses and so on. So probably if you have a chemical reactor, let's suppose that you have a chemical reactor. Okay. And you have here some broth, some liquid. You do some agitation, okay, so that this is stirred, so that you don't have to worry about inhomogeneities. And you have a valve. And you let something coming here, okay? And suppose that this is you have some chemical product A that decomposes into B plus heat. Okay, and you are removing. So this has a name. Jose, what is the name of this? You know?
What?
You are steering. I don't display the
stirrer, the bioreactor, the outline.
So if you have a reactor that is stirred complete so that it is homogeneous, you are continuously inputting something, and you have a tank. This has a classical name.
A continuous process.
Continuous stirred tank reactor, CSTR. Okay, this is curiosity. CSTR. So continuous stirred tank reactor. Continuous because you are continuously adding something and removing, and there is a reaction here. And it's stirred, so the stirred is not just for the folklore, it's because everything is assumed to be homogeneous. Now, you are doing your reaction, very happy. And since this produces heat, so you put here a jacket where you put some cold water. So there is a valve, again a valve. And you inject cold water. And you have an output which is hot water. Okay, so this is your physical process. And you want to keep the temperature constant, so you measure the temperature. Somehow you have, you are measuring here the temperature. I mean, you don't measure with a thermometer, but I put a thermometer. So you have the temperature. The temperature, okay? And you want to keep it still. You want to keep it still. So, and so you want to control the tank, the reactor, the temperature, okay? Keep the temperature at desired point, desired value, okay? So how can we do it? We get a PhD student, and then what do we do with the PhD student and the reactor? So we have the PhD student here. Usually they come from Iran, but they may come also from Lisbon. It's or from India or whatever. I mean,
Or from the Azores.
or from the Azores.
Yes. Tonight is a
Jose today will
game.
be divided because
yeah.
his two loves are going to go one against
Exactly.
the other. Okay.
Exactly.
So we have a PhD student, and what does he do? What does he do? To keep the temperature still.
It turns on the cold water.
So
If the temperature rises
okay,
above,
so he looks at the temperature. He looks at the temperature.
Yeah.
Okay. And then what does he do?
Based on the temperature, so he or she needs to add the cold and the hot water in.
So he adjusts this valve. Okay.
Yeah.
Okay. So this is a control system. Okay. You have a sensor. You have an actuator. Of course, you have a process, which is a reactor and all that stuff. Okay. And you have a controller. And you can represent this in a way by block diagrams. So you have your process. And so this is your process. And you can describe the process by a set of differential equations. Okay? You can describe your process by a set of differential equations. And you measure some variables. So let's call y the variables that you measure. Okay? And then you have a number of variables. In this case, you just measure y is equal, it's just the temperature. And you have your control variable or manipulated variable. Okay? So the manipulated variable is something that you can impose. I say that this is imposed by the outside world, so I call this an input. It's a manipulated input because I can adjust it from the outside. Then you have an output, which is something that is generated by the process to the outside. We call it an output. Okay, this is nothing new because you know how to describe. No, you know how to describe x dot equals to a x plus bu. Okay, y equals to cx. So this pair of equations relates the input with the output. And then you, oh good Lord, I should have written this in red, but okay. I'll use some other color. Say, we have something that receives information from the temperature. So somehow here you have a sensor. Okay, what is a sensor? Here is the temperature. In here is the temperature. The physical variable is here. Physical variable. And here it's perhaps electrical variable, say tension or electrical tension, electrical variable, proportional to the temperature. Okay. Usually this electrical variable in a industrial setting, this is a current. Okay, it's a current because of practical reasons to avoid contamination by noise. But it's better for us to think about tensions, electrical tensions. So it's a tension between minus 5 volts and plus, or minus 10 and plus 10 volts. Okay? And your temperature is something where you have it. Of course, you don't work with a negative temperature. So your temperature is, I don't know, 80 degrees or 70 degrees or, okay? And now you have this is your controller. Here we are again. This is our controller. Okay, in the controller, and you have a reference. You have a reference here. The reference is the desired temperature. So this is the desired temperature. Okay, so what is a controller? A controller is a rule that knows the desired temperature, looks at the real temperature, and somehow computes the manipulated variable, which is the valve. And this can be done in many, many ways. Some are very simple. Some are very sophisticated. In biological systems, you may not have, well, in some cases, you can have a biological reactor, but you can also have, for instance, inside us, we have a number of control systems, very important control systems. Do you know of some control systems that we have in our body, embedded in our body?
Control systems.
Yes. That
Fever.
are embedded in your body. No
Fever.
one places it there. The good Lord made you with these control systems. Without that, you can't live. One example.
You have vasoconstriction, vasodilation.
Vasoconstriction and vasodilation. Usually that is in cascade with another more even that serves a purpose. What is that purpose?
Fever.
In general?
Inflammation, hemostasis.
What do you mean by homeostasis?
Sorry?
What do you mean by homeostasis? Homeostasis.
If there is a change in the equilibrium of the body, there will be processes which will counteract this change.
So one variable that you know that for sure should be controlled.
The temperature.
Temperature, good Lord. Okay. We have
fever. Yeah, that's what I said, the fever. Okay,
because there is another thing which is disturbances. Disturbances. Okay. And imagine that consider of Eskimos that live close to in the Arctic with temperatures of -20 or -30 degrees Celsius. And you have people in close to the Ecuador with temperatures that are close to 50 degrees or 40 degrees or no? Or even in the desert, you have, I'm sure that in Persia, in Iran, you have places where during the day you have temperatures of 40 or 50 degrees, and during the night you have -20 degrees, for instance. And the temperature of the body is usually, if you are healthy, is 36.5. That's it. With a small variation of a few tenths of degree. Okay, so the environment temperature are disturbances, and your body has inbuilt control systems, very sophisticated ones, that allow you to keep your temperature still. And this passes, for instance, with the story of vasodilation or constriction, and so on. Okay. Another example is the control of the level of calcium in the blood, in many other things. And we have completely filled with control systems, many. Okay, all our physiology is controlled by control systems. Okay. Now, how can we make a controller? So how can we make this? Ideas. Be an apprentice of God. Okay, you have to control the temperature of your, well, not your body, but your chemical reactor. So you have the story of the hot water, of the cold water coming in, and you are losing energy, so you have to counteract it. So how can you, or if you don't want to stay all your life looking at the temperature and adjusting the valve, how can I program a computer that I can connect here? Okay, for that I need here is, what device do I need? If this is a computer and this is an actuator, I have here an actuator. What device do I need? Cave. You know that? Maxi, you know?
No.
It's an analog to digital, a digital to analog converter. Okay, so here I have a DA. What is a DA? Your computer gives you a number, and this number is converted into an electrical tension. Okay, you can. This is something that you can buy and plug in your computer. Of course, if you have some industrial equipment, you don't buy this cheap boards. You buy something. Okay, but it's the DA converter, digital to analog, is something that transforms. It's connected to a port of the computer. A port is where you can write. It's a kind of position, memory position where you can write numbers. And the DA transforms these numbers. It has an output to an electrical tension. Then the electrical tension will be connected to the actuator of the valve. The valve has motors, has a number of things. Okay, and to receive the data from the sensor outputs some electrical tension. So you have here the inverse, which is an AD. Okay, it's an AD converter. So converts an electrical tension to a digital number connected to the input port of the computer. So a port of the computer, think of it as a position of memory. You can go to memory positions are numbered 1, 2, 3, 4, 5, 6. Okay, not exactly like this, but you can think of it like this. Okay, and save. Position number 10 is an input port. So if you have an AD connected to port number 10, you have an instruction, read port number 10, and it goes there and reads. Okay, and what is there is a number proportional to the tension that comes from the sensor. The opposite is true. Okay, say position number 11 is an output port, so you can write on it. You connect a DA, so you write a number, and this number is transformed into an electrical tension, and this electrical tension then excites a motor, the motor related to the valve, or usually valves don't have motors. It's compressed air. It's an electromechanical device. But okay, let's think about that. If you give it an electrical tension, they work. They do what you want. Okay. Usually, valves are excited between 4 and 20 milliampere. Okay, so this is fully closed. And this is fully open. Okay, so if now you have to codify what you mean by 4 milliamperes, but you can do it in software. Okay, you can do it in software. So this is the overall picture of a control system. And a controller is nothing more than software. So you can write your rules, write everything. Once it was electronics. You can also do it with electronics. Okay. Just let me. So what rule can we place here to keep the temperature close to the desired value? So let's call R is our reference and T is our measurement. So possibilities to keep the temperature still. No ideas. Where is your creativity? We are, just to tell you, about 400 years ago. Okay, the first guy who invented such a process was to keep the temperature for eggs, uma chocadeira automática, 1600 e não sei quanto. Okay, and with the technology of the 17th century, he could do a control system to keep the temperature more or less constant for the eggs. Okay, so 400 years we are still 400 years ago. Okay, not rocket science probably. So what can we? Don't you think of something? What would you do if you were there? What would you do?
Compare the R with T.
So compare, what you mean comparing?
I was thinking about, so if we compute the value of R minus T,
Okay.
and then if T is above R,
Then,
that value will be negative.
okay. And you do what?
So depending on the differential equation, we can make it.
So you can have a rule when R minus T is negative, that means that T is above R. Then
We want
what
to
you do with the
decrease.
water? This is if the sensor gives something, then in this case, if R minus T negative, then value of the actuator. No ideas? Close the water. No, open the water. If the temperature is above the reference, open the water as much as you can. And if the T decreases below R, close the water. No? If the temperature is too high, open the water. If the temperature is too low, close the water. You do like this, but you should have this is. I won't say it's obvious, but almost. No. Okay, so what happens? What happens? Can I clean this stuff here? This big mess?
Yes.
Okay. So let's try to do. We have our block diagram. So I subtract, I have here R, I have here minus the temperature. Sorry, let me. Estou no meio de uma aula, diz lá. So I have this rule that I call on, off. Okay, and then I have my U, and I have my temperature. And I'm omitting the sensor and all those stuffs. Okay, so in some units, I'm comparing the signals. And this is my plant, my reactor. Okay. Now, I also called here an error. So E E is the reference minus the temperature. Okay, I call this the tracking error because you want to track R by T, but you are in error, so this is the tracking error. Erro de seguimento. Okay. Now let's do some qualitative plots. So I have my reference. This is the temperature, and this is time, and this is the error, and this is U. Okay, and we have a reference, so I write the reference in red because it's our target. Suppose that the reference is here. And you start with the temperature, which is here. And here you have your error. So remember that the error is R minus T. So where am I? Here, this side, or this side? Where is the first position of the error?
It should be 0, no?
0? Why 0? 0 means R
The
equal to
reference
T.
equals to temperature.
No, but when you start, your temperature is here. Okay, this is your temperature.
Okay, so it's
The
negative.
red one is the reference. The red one,
Okay, so it's negative.
this is the value of the reference.
Okay, so then it's positive. So it's positive.
So E is positive, is here. And according to your on-off rule, what you do? You open the valve or you close the valve?
You
We close it.
Close
Close
it.
it.
You
Okay.
close it. So the valve is closed. Okay? The valve is closed. So this is 0, and let's say it's 1. 1 is fully open, 0 is fully closed. Now, so you don't have any refrigeration. What happens to the temperature?
Goes up.
Increase.
Goes up. Sets go up. And the error
Goes down.
goes down, which is it's exactly this difference. There is one moment in which you reach this point. So the error at this point is 0. And initially, what is the value of your control? The temperature is below the reference.
It's 0.
It's 0. Up to when?
When R is equal to T.
When R is equal to T, and probably, since it has the reactor has some inertia, it passes. So what happens to it? It passes. So at this moment, what happens? With
It
you,
goes to 1.
it goes to 1. Okay, and when it goes to 1, it starts probably decreasing. Okay, it starts probably decreasing. And when it reaches this value, it comes down. So this was decreasing, but then it increases again. And when it increases again, you have something like this, and this becomes 0, then decreases, increases, goes there. Okay, so you have this, you have a kind of oscillation. You are keeping your temperature close to the reference, but not much close with this on off, because you are switching your valve. Okay, and the temperature goes, decreases, increases. Okay, this is a thermostat. But if you buy a electrical heating equipment, it has a thermostat works exactly like this. So we could probably improve this result. You have ideas for improvement. What is the reason for this oscillation?
The reason.
Yes. Why does the temperature oscillates?
Because must be a delay. Is when you open the cold water.
Yes, there is probably some delay, so the inertia and so on, but there is something in your strategy that causes this oscillation. Suppose that you were free. Suppose that you were free to adjust the valve. The valve was not just fully closed or fully open. What would you do?
You will change the flux.
You would adjust the flux in order for what?
In order to keep the temperature constant. So
And that is achieved by what? I'm entering your domains, okay? That's thermodynamics, very basic thermodynamics. So what would you do? You have your ejected reactor. You are producing energy, and this energy in the reaction causes the temperature to rise because of energy, thermal energy being liberated. And you are removing it with cold water. So how can you come to a situation? Is it possible to come to a situation in which you have the temperature still by adjusting the flow of cold water? What is the condition in thermodynamical terms?
The input, like the hot water and the cold water, must be adjusted together. I mean, they must be equal.
Not the cold water. The flow of water should be such that the energy removed by the water, which is proportional to the flow, should be equal to what? The energy removed by unit time should be
equal to the input energy. So
to the energy being liberated by the reaction. Okay. So what would you try to do? You are at a lab and you have the reactor and you have this valve that you can adjust manually. What would you do?
First, measuring the output energy. So then we will set the.
But you don't have equipment to measure the output energy. That's too complicated, and then you have to, in practical terms, you are there, you will have to stay there all the night adjusting things. But you want to sleep for at least periods of 2 hours instead of being continuously awake. So what do? You don't have all this equipment and you don't know how to do the computations. So what do?
adjust the valve,
Adjust the valve such that what?
the temperature. is
The
equal to
temperature is
desired-
kept still. So there is a point. There is a point. We don't know what point is, but maybe we can select here one value between 0 and 1, between valve fully open and fully closed, such that this temperature goes to the correct point. Okay. Now, you can do it. How do you do it? You do it by looking and by trial and error, and you do things. I mean, if you have a big error, you do a big change in the valve. But if you have a small error, you just do a tiny adjustment in the valve. So instead of having here an on-off, what would be probably reasonable to have? Something that gives you this continuous adjustment. What could be this continuous adjustment?
A valve.
Huh?
A valve for
The
the.
valve is there. I mean,
Okay.
you are speaking about your controller. Your controller is the ruler
Mm-hmm.
to control the valve. That's the key point.
It's
You have the valve, you have all the hardware, and you want to say, I want to replace my software. And my software is very simple here, such that for big temperature errors, I do a big action. For medium temperature errors, I do an intermediate action. But for very small temperature actions, I just do a small correction. No ideas of a mathematical operation that you can place there? What mathematical operations do you know?
This is, I think if you want to maintain the temperature constant, then is a derivative, no? Of the temperature across time should be 0 or near 0.
You suggest that instead of having here on off, I put here a derivative. So this should be a differentiator. Okay? That's your theory. When I say okay, it's okay to your theory. You would be dE dt. Okay? So you would be dE dt. Let's see if it works. Suppose that E is constant, in particular that E is 0. What is the output of the derivative?
0.
0. So it closes the valve. You don't go there. Okay? So with the derivative, you don't go there. More mathematical operations. Simpler mathematical operations. Can't you think of something simpler? And the derivative is not a question of an issue of being complicated. It does not work. You understand why? You agree with me that it does not work?
Yeah.
Okay. So something that places here, you want to change the valve in a way which is proportional to the error. So what mathematical operations do you know?
It should be proportional. Then
And so
E over U is equal to 1.
So you say that E is equal to U.
Yes. Yes.
Why? That is to say, U is equal to E times 1. So I put here 1. Okay? Now, let's test your theory. Okay, so T, let's suppose that you are in steady state. That is to say, that this thing evolved to a constants. So T is constant. And you call G the gain of the plant. So T is equal to GU. And these are numbers. Of course, they have units associated, but let's suppose that you somehow normalize this so that you can compare everything. Now, U is equal, how do you relate U with E? This is G in terms of E. What is the relation between U and E? This
They're
is a very,
equal.
they're equal. So this is G times
E.
E. But now, what is the relation between E and T? There is a relationship.
R minus T.
R minus T. So you have that T is equal to G R minus T. And this means that T 1 plus G 1 plus G is equal to GR, right? That is to say T is G 1 plus G R. Okay? Is this very difficult mathematics? No. I will teach you a trick to know what is the relation between T and R in a moment. But for the moment, I mean, this is just algebra. You agree? Any doubt? Kaveh, are you following me?
Yes, exactly. I am following.
Okay. No. Conditions for T to be close to R. G is a number that describes the plant, okay? So we can't change it. But in what conditions does this control law yield something such that T is close to R?
When G is higher than 1.
G very big. G much higher than 1. Because in that case, this becomes, can you complete your reasoning, Maxi?
I was thinking about the limit of that term.
Okay,
G
so
divided by 1 plus G.
G is much bigger than 1, G plus 1 is approximately G, and G divided by G is 1. Okay? Now, we have a problem, and the problem is we can't change G. If you could go there and increase the gain of the plant, but no, that comes from the chemical reactions. I don't know what is the value of G. We don't know. So the only thing in which we can change is the controller. This is the only place that we can change because this is physical, okay? And this part here is software. So you can only change here. You cannot change there. So can you modify your controller? Your controller is just one, U equal to E. Okay, can you modify this rule such that you somehow save the day with respect to this theory?
We can say U is a constant times E, and then
So I
choose
put
the
a
value of that
constant
constant.
here, and Maxi says, let's use orange, put a gain, okay? Put a constant here. I call it K, okay? So let's see what happens. In this case, what do we have? What do we have? We have T is equal to GU, that's right. But then, what is the relation between T and E?
Now it's G
Now
K
it's G.
G times
K E.
KE, okay? And this is what? G, K, and then expressing T.
T.
R minus T.
R minus T. And this means that T, and then I have this other term, T. So I have T is G, K, R minus G. I mean, you should be ashamed of not doing this computation so fast. Okay, so T 1 plus GK equals to GKR. And this means that T is GK 1 plus GK, and this multiplies by R. So what is now the condition for T being close to R?
GK must be
GK must be
much higher than 1.
much bigger than 1, that's right. Okay, this product as a name, it's a loop gain. Okay, so it's the product of the gain of your computer, which is K, and the gain of your plant, which is G. Okay, so what you do is you place here a number, a gain, proportional gain, yes. And in this way, you are able to converge to a value which is not exactly R, but it's very close, provided that GK is big. And in G you can't change, but you can adjust K. Okay? Now, questions? Is this clear up to now?
Mhm.
You are very rusty about doing simple algebra.
Yes.
For what value of K would I have T equal to R?
Infinity.
Infinity. Okay, but we can't place an infinity in computers. I mean, in MATLAB you can write inf, no. I think you can write, you have the infinite number, but it does not work, okay? But we are going to see that we can have a trick that amounts to have an infinite gain. Let's see what happens in terms of the evolution of things. So let me clean this stuff. Can I clean this?
Mhm.
Yes.
And let's do our plotting. So we have the temperature, and we have the reference, the temperature. And we have the error. And we have U. We have our reference. So we start here. We have some error, which is here. And now we don't have a new, which is 0. We have a new, which is proportional to the error. Okay. Actually, this is KE. Now, what happens? The temperature increases and the error decreases, and your U decreases smoothly. Okay, it's not always, it's not still on and off. Okay, and then you end up with a small error. Okay, so this comes for a small error, and your U is kept here. Now, what would happen if T is equal to R? What is the value of E if T is equal to R?
0.
0.
0.
Zero.
And what about the valve?
Also 0.
If it goes to, if E goes to 0, okay, U goes to 0, and then what happens here?
Goes
What
up.
happens here? Up. You close your valve, it goes up. That's right, because it's an inverting. Okay. So you can't have U equal to 0. You can't have a 0 error, because a 0 error forces the valve to close. You see?
But that's interesting.
Okay. So we have this problem. I mean, there is a limit in the error. There are many. Of course, we can go without it. Now, we could place here an infinite gain, because an infinite gain, infinite times 0 gives you, it's an indetermination. So we have to replace this controller by something. We have to replace this controller by something that probably we can do in parallel. This what shall we put here such that when E is 0, well, if E is 0, this is no longer there, but this keeps you at the correct point. So again, mathematical operations that we can place here. Differentiator, if E is 0, the differentiation of a continuous 0 is again 0. So differentiation is ruled out immediately before you say. So alternatives.
Add a constant.
A constant, we have it there. It does not work. No?
But can we sum like E plus something?
What do you mean E plus something? Can you think of some mathematical operation that when the input is 0, this keeps at a still value, it keeps still. Input 0 and output a constant. Enough so that you are at the correct point. The valve is open enough so that it compensates the energy that is going away.
That
I think that's
something
how functions. Tell me, Kaveh.
it is like functions or something that would related to the k infinity. So it would be like
It's not a fixed function, because you want to have this as a function of the error. Okay, you don't want to do to put here something which is a precise value, because if you place a precise value, and if your reactor is a little bit bigger or a little bit smaller, that precise value would not be the correct one. So you want to have something that is robust, that self-adjusts. So adding a constant is not a good choice. It would work if you have if you could do all the precise computations of the energy and so on. You compute the precise value of the valve and you put it there. But then the night was too cold or colder than what you expected. This constant would not work. So you have a disturbance. Disturbances do not. We can do some computations like this to see what happens to disturbances. But alternatives. So not a differentiator, not again a constant gain, not a constant that is not a gain, just adding something. So other possibilities. Well, the trick is an integrator. The trick is to integrate this signal. The trick is to integrate this signal. Okay, so you put here an integrator between the moment in which you start and present time. And you integrate the error. Okay, what happens? The integral is the area under E, is this area. Okay, when E goes to 0, and the integral is going to change. When E goes to 0, what happens to the output of the integral? When E becomes 0, what happens to the signal here?
It's constant.
It's constant. And this constant is, you can show it's the correct constant, provided something happens. I will tell you in a moment what is the condition. But this constant is, an integral can be seen as an infinite gain. What is a gain? What is a gain? Let me clean this stuff. A gain, if you have an input signal, let's say E, and you have a system which is a gain, then you have a nu, which is Ke, okay? If this is time, this is E, then suppose that this is 2. Then what you have here in the output?
K.
Ke, okay? 2K. Okay? Now we have an integrator. And again, you put E. And this is an integrator. what happens? And you start with a 0, the integral is initially unloaded. The initial condition of the integral is 0. So what happens?
It starts increasing from 0.
So you start from here and starts increasing in which way? Like this? Like this? Like this? E is that constant. What is the meaning of the integral? What is the
It's
meaning of the
the
integral?
area under the curve.
It's the area under the curve. So if you are at time t, the integral is this area. Okay, so when t grows, it's the area of a rectangle that grows with t. So this goes linearly because the input is constant. So it is something like this. Okay. Now, the output here, in this case of the gain, the output reaches immediately steady state. Okay. When does this signal reaches a steady state? Quando é que este
When-
sinal que está sempre a crescer atinge o estado estacionário?
When E is equal to 0.
When?
When E goes to 0.
I mean, you have E which is constant, equal to 2. And your output is always growing. When would you say that this reaches a constant value? One possibility is say never. Another possibility, which is a little bit more sophisticated, is what? When time passes, this is always growing. No?
Yeah.
So when does it stop?
Never.
Never. We learned some mathematical tools to deal with never.
Infinity.
Infinity. At infinity, and it reaches what value? What is the value of this output when t is infinity? What is the value? Of course, this will never happen because you can't wait an infinite number of an infinite time. You will die before. Me too. All of us, I mean, even the earth will disappear. But in conceptual terms, what is the value of the output when t is equal to infinity?
Infinity.
Infinity.
Yeah.
So what is the gain of this, or what can you say it's the gain of this integrator? It's an infinity gain. Okay. And this does the effect of an infinite k. That's why the error becomes 0. I mean, this is perhaps very elaborated, too much elaborated. But one thing is you can really understand and accept without any argument, which is the integrator, when the error is 0, the integrator output is not 0. And that is the trick that allows you to keep u at the correct value so that t is equal to r. Okay, this is a proportional integral controller. This is a proportional integral controller. That's a PI controller. Okay, all the factories have a lot of PI controllers. Most of the guys who speak about control, they only know of one controller, which is the PI or the PID if you add a differentiator. Okay?
Okay.
Now, questions about what we have been seeing? So let's change this. Let's go back again to our proportional controller. And let's see what happens when we have a disturbance. So the disturbance means the temperature of the night, of the day, or the environment was with some value and it changed. That's a disturbance. Or you are keeping an airplane at a constant altitude, but then there comes a wind gust and it starts shaking. That's a stochastic disturbance. Or you have a solar system and you want to control the temperature, but then a cloud passes. The cloud is a disturbance. The radiation is a disturbance. Okay? So let's clear everything. And so we have what? We have our reference. We have our gain. And we have our G, but then we have an extra signal, which is our disturbance D. And this adds. You can say, well, I can have D at the output or D at the input. Can happen. Let's consider it at the output. And then we have the feedback. This is a feedback controller. Okay? And let's assume that our reference is 0. Okay? We can say, well, consider that you are linearizing about some value, and reference 0 means you are at equilibrium point. You have a nonlinear system and you are linearizing. So now, and you have your temperature here. How can I relate T with D? What shall I say? Some mathematics, simple mathematics. T is equal to this is E, this is U, and this I don't say. So T is what? This signal here comes from where? You don't understand the meaning of the block diagram.
It's the addition of D.
It's
with-
what?
It's D plus
D plus
GK
G K
R minus T.
R minus T. Good, very good. So T is equal to plus gkt is equal to d plus gkr, but r is 0, so we don't have it. Okay, so t is equal to 1 plus gk, okay, g, whatever you want, you can interchange it, d. So how do you design k? How do you design k such that, how do you design k such that you want to have t insensitive to d? D changes, but t does not change. So how do you select your gain k?
Much bigger than D.
Much bigger, such that gk is much bigger than 1. Okay, so gk must be much bigger than 1. Okay, in that case, if gk is bigger, then 1 over a bigger thing is t small. Okay, so by having a loop gain I, you have reduced the influence of d on t. If you had no control, t would be proportional to d. T would be, the influence of d would be something, okay? But now it's attenuated by this factor. With control, it's attenuated by this factor. Do you understand this? I mean, you wouldn't be there if it were not for this fact. Feedback control was something essential for modern society, although we don't appreciate it. Okay. So, what is the rule to make t track r? So t close to the reference. This is obtained. What is the condition of k? Big, small, medium, blue, made of crystal, big. T close to 0 or to the value that it had when tracking R due even if R different from 0. What is the rule about K?
Is small?
No, big.
Big.
If K is big, 1 divided by a big thing is close to 0. So again, it's big. Okay? Now, I wanted to think of something. And that is your homework. Suppose that you have a sensor. A sensor, you model it by noise. So you add here something which is N. And this is sensor noise. Okay, this is sensor noise. And so what is T assume that D is 0, that R is 0. So what is T as a function? Of N. And how should be should K be? Okay, so what you see that here, at least in simple terms, then we are going to see that these things should be more careful. But in general, when you do a feedback, at least for simple cases, you just need a big gain to track a reference or to reject the disturbance. Now, what happens to the noise? Should K be big, small? What should it be? Medium? That's your homework for next Wednesday. You understand? So do a similar analysis, compute the temp T as a function of N, assume D equal to 0, R equal to 0, compute the influence of N on T, doing the same computations that we did before, and then make some conclusions about what range of K, what is the range that K should have to, so that the sensor noise does not affect your T. What do you expect? What do you expect? Do you have any expectations? No, you don't have it for the moment. So this is, you understand the work to be done? Okay. So we stop here.